Hello, welcome back. So today I will show how to use our tool DANTE. DANTE is a tool for annotation of transposable element protein coding domains. You can use it on contigs or on genome assemblies, and I will also show how to interpret the results from DANTE and how to make visualization in a genome browser.
DANTE pipeline utilizes protein sequences from RexDB database to annotate protein coding sequences in a transposable element in either contigs or whole genome assemblies. Similarity search is performed using last program, and all similarity hits which pass the initial threshold are then recorded, and resulting annotation reflects the RexDB annotation and all hits which were above the threshold. And then the resulting final annotation can be either determined to a specific classification level or to some upper level classification if some ambiguities exists. In this demonstration we will use a genome assembly of cocoa tree. This genome is rather small, approximately 345 megabases long, and the annotation with DANTE should take no longer than a couple of hours. First, create a new history and name it accordingly. I will name it DANTE analysis. Data for this analysis are available in the shared data libraries. Go to workshop 2021 data and select DANTE directory, and data within this directory should be imported as a data set to already prepared history. In a while these data should be available. There are two data sets. First one is a FASTA file with a genome assembly, and the second one is a GFF3 file with a gene annotation, and we will use this data set later. In the DANTE section, find a tool named Domain-Based Annotation of Transposable Elements, and keep all options at default values. In the most cases, default values will work best for most of the DANTE species, but if you are analyzing metazoa genome, you need to change the RexDB database accordingly. However, you should be aware that the metazoa database is not as comprehensive as a DANTE database. If your species is evolutionarily distant to species covered in the RexDB database, you might consider to test search with a Blossom62 scoring matrix, or even using iterative search. In this tutorial we are using as input genome assembly in a FASTA format. There is however also option to provide assembly files in ACE format. This option is intended to be used if you want to analyze contigs from RepeatExplorer pipeline, and in that case, if you use ACE as an input, then the information about the read depth of the individual contigs is used and reported in the resulting annotation. And these numbers later can be used to estimate copy number of individual lineages of transposable elements in the genome. Now, when the options are set up, we can hit start. DANTE analysis of complete cocoa tree genome should take approximately 3 hours. Dante creates by default three output datasets. The first dataset is a full Dante output in a GFF3 format, which include all regions which were detected using a similarity search. This output can, however, include some low-quality annotations and spurious hits. These low-quality hits are removed from filtered output, which is again in a GFF3 format. And by default, only regions which has at least 35% similarity and 45% identity to the reference sequence in the RexDB database are kept. And additionally, alignment must be over at least 80% of the length of this RexDB reference, and also the number of frame shift and stop codons must be kept below a threshold. And the last output of Dante is a FASTA file with protein sequences which were translated based on the Dante annotation. This output is suitable if your aim is to perform phylogenetic analysis of transposable element based on the protein sequences. Now let's take a look on what information we can find in the output, which is a GFF3 file produced by Dante. This is a standard GFF3 file which contains all mandatory information, and also it contains some Dante specific information in the attributes column. This attributes column is the very last column in GFF3. The type of the detected protein domain is in the name attribute. In this case, it's a GEC protein. Then final classification attribute contains a resulting annotation created by a reconciliation of all hits to the RexDB database, which were above the threshold. The classification of all these hits are listed in the attribute which is named region hits classification, and note that this attribute can contain actually multiple values if hits to more than one repeat lineages were found. Then the best hit attribute point to the record in the RexDB database. So this is the protein which yielded the best similarity hit to the queried region. And the best hit database position tells us what part of the protein from the RexDB database was aligned to the query. So here we can see that the length of the protein which made the best hit was 93 amino acids, and it was fully aligned to the query. Amino acid reference sequence from RexDB and corresponding translated sequence from the query are also part of the attributes in GFF. Quality of the alignment of the query and reference is described by identity, similarity, and also by a relative number of the interruptions. The interruptions here means it's a total number of the stop codons and frame shift per 100 amino acids. Now, when we have a resulting GFF, we can create a simple summary table where we will summarize number of individual lineages. We will use a tool named Summarize GFF3 output from Dante. Here you can summarize it based on the different features, either based on the classification or domain name or a sequence ID. Sequence ID in this case is the chromosome ID. So we will choose a classification and just hit execute. The running time for this tool should be rather short. It should take several seconds. Now we can see the table with summarized hits per lineage. You can see that most hits were found for sire lineage and TK lineage. In some cases, classification was not determined to the specific lineage, but you can see that the number of such hits is rather small in comparison to the number of all hits. Note that the numbers here reflect hits to all domains. So, for example, in the case of sire element, it's 5 domains: GEC, protease, integrase, RT, and RNase H domain. And from this, we can make a rough estimate of total number of sire elements. 1/5 of the number of hits is about 1,000. So we can say that there is about 1,000 of sire elements in the cocoa genome assembly. This estimate is, however, very approximate, and it doesn't take into consideration the presence of elements with incomplete protein coding domains or non-autonomous transposable elements which does not contain any protein domains. If we want to summarize number and type of detected protein domains per lineage, we can rerun the same tool again and add category which should be summarized. Here I will select also a protein domain name. Again, to create this summary, it shouldn't take longer than a few seconds. And now, when you find again sire elements in the table, you will see that there are approximately 1,000 of hits per each protein domain type. GFF output from Dante can be downloaded and visualized, for example, in an integrated genomic viewer, or it can be viewed directly on the Galaxy server in a Jbrowse genomic viewer. Here I will show how to create such a Jbrowse instance with your data. First, we will create some subsets of GFF3 files so we can see separately copia and gypsy elements, and also some abundant lineages. To create such subsets, I will use tool protein domain filter. This tool can be used to filter Dante GFF output based on the quality of the hits which are stored in the attribute columns. So, for example, it's possible to filter based on the similarity, identity, alignment length, and other criteria. It is also possible to select a subset based on the protein domain type and final classification attribute, which we will use here. As input, we will use DANTE filter GFF. The other option will be kept at the default values, and then choose type of classification we want to keep in the output. Enter classification must match exactly a substring in the final attribute classification, and keep in mind that the matching is case sensitive. Then we can rename the output so it will actually match selected classification, and then you will repeat this procedure, and we will gradually select gypsy, copia, TK, sire, Ivana, and ogre elements. Also rename always GFF output, as this name will be later displayed in the Jbrowse genomic viewer as a track ID. To run a tool again, you can either choose the tool from the tool menu, or you can use rerun button. In case you will enter a string which does not exist in the final classification attribute, then the tool will end up with error. So make sure that the string you entered is correct. Each filtering step shouldn't take no more than a couple of seconds to finish. At the end, you should have 6 additional GFF3 files. To see them easily in your dataset panel, just type GFF3 to the search window and hit enter. When we have ready data for genomic track, we can use a Jbrowse tool. As a reference genome, you will use a genome from history. And then we will create a track from gene annotations. This is the track we got at the beginning from shared libraries. As a Jbrowse track type, select canvas feature, and then we will create a new track group which we will label DANTE, and we will include all DANTE GFF3 datasets. And again, we will set track type to canvas feature. And when everything is ready, we can just hit execute. Execution time for this tool depends on the size of the reference genome and then on the number and size of tracks which are included. Usually it takes several minutes to finish. Now we can open Jbrowse genomic browser, ideally in a new window, so we can fill full screen, and you can inspect available tracks. When the number of annotated feature is high, then the track is visible as a density plot. If number of annotated feature is lower, then we can see individual features. Here you can see nicely a negative correlation of the gene and transposable element density, as the number of annotated gene is lower around centromere, which is here approximately in the middle of chromosome 1, and transposable element on the other hand are more concentrated around the centromere but absent in the gene-rich regions. When number of annotated features is high, then the track is visible as a density plot, and if the number of annotated features is lower, then you can see individual features, as in the case of the sire, ogre, or Ivana lineages. Here you can also observe that the distribution of individual lineages along chromosome can differ. For example, Sire lineage here is more often located around the centromeric regions, while Ogre and Ivana are more evenly distributed along the chromosome. So DANTE can enable us to study this lineage specific properties. If you zoom to smaller region, you can start to see clusters of domains. These clusters correspond to domains from a single element. If you click on the track, you will see corresponding annotation. So for example, here we can see domains from Ogre element, which contain a complete set of protein domains. The other element we can see is Icaros, and here we can actually see that integrase and reverse transcriptase domains are duplicated in this element. Quite often you can also find elements which does not contain full set of protein domains, like this one, which contain only protease and GEC protein, and it's part of the TORC element. Or here where you can see the element which contain protease, integrase and reverse transcriptase, and all are from a Bianca lineage. So DANTE enables to distinguish autonomous elements from non-autonomous elements. If you will use a DANTE program, please cite Pavel Neumann's paper, which describes transposable element annotation system, and also our RepeatExplorer server. Source code and command line version and also basic documentation for DANTE are available on GitHub.